Hi everyone, this is first lecture on algebra. This course is specially designed for the student of B.Sc second year. The content covered in this lecture is binary composition, definition of binary composition with various examples, definition of group, groupoid, semigroup, monoid with the help of examples. So before discussing the definition of binary composition, let us start with let A be a non-empty set. Non-empty set. Then we define the Cartesian product A and B be two non-empty sets. Let A and B be two non-empty sets. Then we define Cartesian product of A and B be A cross B, that is order pair AB, such that A belongs to A and B belongs to B. So similarly, for example, if we take A to be 1, 2, 3 and B is 4, 5, 4, 5. So A cross B is A cross B, we define A cross B by this. So A cross B is, it contains elements in the form of order pair. So 1, 4, 1, 5, 2, 4, 2, 5, 3, 4, and 3, 5. So these are the elements of A cross B. So number of element in A is 3, number of element in B is 2, so number of element in A cross B is 6. 3 to the 6, 3 into 2. So similarly, A cross A is defined. A cross A can be defined. A is 1, 2, 3. We have to take the Cartesian product with A. So we get 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. So these are the elements in A cross A. So similarly, you can try B cross A, and B cross A is not equal to A cross B. You can check. You can find two order pairs are equal. AB is equal to CD if and only if A equal to C and B equal to D. So in A cross B you get 1, 4, and in B cross A you get 4, 1. So 1, 4 is not equal to 4, 1. So A cross B is not equal to B cross A. But in A cross A, it is equal, right? So now the elements of A cross A is of the form A cross A. You can take the element in the form of A comma B such that AB belongs to A. Is it clear? So element of A cross B is in the form of order pair. Okay, now come to the definition. Again, important point to all of you, revise the definition of function. Definition of function. Because it is very, very helpful to you in algebra. So quickly discuss what is function. Let A and B be two non-empty set, and F is a mapping that associate element of A to unique element of every element of A to unique element of B. So every element of A has unique image in B. So in this way we define function. So now come to the definition. Binary composition. So up to this, I hope how we can define Cartesian product. And second important thing, you have to go through the definition of function. So these are the prelim part for algebra. So if you are confident that you know the definition of function and Cartesian product well, the concept is good, then definition of binary composition and other definition of algebra become easy to understand for you. Okay. So binary composition, let G be a non-empty set. Binary composition on A, not A, it is G. On G is a mapping, F from G cross G to G. So G be a non-empty set. So binary composition on G is a mapping that define F from G cross G to G. So all of you know that how we can define the G cross G. G is a non-empty set, it is given to you. So first we define G cross G. The element of G cross G is in the form of A comma B, where A B belongs to G. It is in the form of order pair. So if we take star be a binary composition from G cross G to G. So this is the domain G cross G, and this is G. We define mapping star from G cross G to G. So element of G cross G is in the form of A comma B. Right? So if we take element in G cross G, then the output we get is that also belongs to the element of G. It means we get A star B. Right? So if we take C comma D, then the output we get C star D. Now this star may depend upon under which operation we are working. If we can take star to be addition, star to be multiplication, star to be subtraction, star to be division, or any other. So the element of G cross G is in the form of order pair. So when we apply the binary composition, operation star on a comma b, then we get a star b. So for each order pair given any a b in G cross G, there exists unique, so I can write this symbol for uniqueness. There exists unique A star B, this belongs to G. Even A star B, no need to write bracket, A star B belongs to B. Every element of it. If we have E comma F, then E comma F must be associated with at least one element. Maybe it associated with C star D, or it must be associated with at least one element. Exactly one element, unique element. Sorry for at least, it is exactly one element. So if we take for example, let us take G is equal to set of natural number. If we take G to be set of natural number, and we take star binary operation addition, we take binary operation addition plus. So we have to show that plus n cross n to n. Is it a binary composition? Yes, you can take any two natural number. So let us take 1 comma 2, and if we add them, we get 1 plus 2. So we replace star by this star by plus. So 1 plus 2 equal to 3, and 3 is also natural number. So addition, if we take the set of natural number, then addition on G is a binary operation. Is it clear? So this is first. So let us check for the same group, same set of natural number. Is multiplication be a binary operation, binary composition? चेक करते हैं क्या नेचुरल नंबर के लिए मल्टीप्लिकेशन बाइनरी ऑपरेशन है. सो यू कैन टेक any two natural number, 3 comma 4 5 comma 7, whatever it is, let it be 3 comma 7. So what is the answer? 3 into 7, and 3 into 7 is equal to 21. So 21 is a natural number, so it is again. So how can we write this? So we can write this as plus. In general, we can take any a b with two natural number such that a plus b also natural number. Sum of two natural numbers is again. Similarly, for multiplication, you can take any a and b be natural number, given any a b in n, such that a dot b is also natural number. So on set of natural number, addition and multiplication, they satisfy their binary operation. Now question to all of you, think about this. Is subtraction from n cross n to n be a binary composition? Is this? No, because if you take 2 comma 3, take 2 comma 3, minus is the binary operation, then the answer is 2 minus 3, that is equal to -1, that does not belongs to n. So it is not a subtraction on natural number is not a binary operation. Think about division. So it's an exercise to you. Think about division. Okay. So now let us consider, let us change the set. Second example. This is first. Second, if we change the set G to be set of integers, that is set of all integers. So again is, if we take binary operation plus z cross z to z, is it a binary composition? Yes. You can take any two integer a b. So sum of two integer is again an integer. So this belongs to a plus b belongs to z. Yes, it is true. Second, you can take multiplication z cross z to z. So AB, so we get A dot B, product of two integer is again an integer. Now think about subtraction. Is subtraction on integer be a binary operation? Yes. In case of integer it is true. But now think about division. If we take 2 comma 3, is 2 by 3 be an integer? No. So division is on, even this is not true because 0 also belongs to z cross z. So we cannot divide any number by 0. So if 0 comma 1 belongs to, or 1 comma 0 belongs to z cross z, but 1 by 0 does not exist. So division is not a binary composition. So now question to all of you. Think about if we take G, so we can write this as, we can take, so we can denote this by, we can say that G with binary operation star is a binary composition. Is a binary composition. So similarly, here n with set of natural number. In first case, n with addition is a binary composition. In second case, set of natural number with multiplication is a binary composition, but set of natural number with minus subtraction is not a binary composition. In this, in first and second case it is true, in third case it is not true. But here z with binary operation plus this is a binary composition, z with multiplication is a binary composition, and z with subtraction is a binary composition. But z with addition, with division, this is not a binary composition. And the example is, if you take any element 2 by 3, the answer is 2 by 3, that does not belong to it. Now, if I question to all of you, think about this set of rational number. Q is set of rational number. Q under addition, Q with multiplication, set of rational number with subtraction, and set of rational number with division. Again, think about this fourth part carefully. Set of rational number with division. and write your answer for this part. This is A part, this is B part, this is C part, and this is D part. Write your answer of D part in the chat box. I will respond. Similarly, if I take G to be, if I take G is equal to set of real number. R is set of all real numbers. So R under addition, sum of two real number is again a real number. R under multiplication, R under subtraction, and R under division. Again, think about this fourth part carefully. Okay. So try these questions. Now come to the definition. Definition of group. To this part, we have discussed various examples which with binary operation, addition, subtraction, multiplication, or division, we form binary composition, and some of them are not. Okay. So now come to the definition of group. A non-empty set, let G be a non-empty set, or a non-empty set G together with or let us change a set G, a non-empty set G G with a binary operation star from binary operation is defined from G cross G to G is called a group. Group if it satisfies the following axioms. It satisfies the following axioms. First is, given any AB belongs to G such that A star B belongs to G. Even there is no need to define the first property. Why? Because it is a binary composition. Binary operation is already defined. So binary operation is defined, and we have already discussed that if binary operation is defined, then A star B belongs to G. Given any AB in G, given any AB in G cross G, A star B belongs to G. So it is given that this is a binary composition. So even there is no need to write this property, right? So I skip this one. I start with, even in some textbook it is given that given any a b in G, so that a star b belongs to G, closure property, but already defined. This is a binary composition, binary operation. So I skip this part. So given any a b c belongs to G, such that a star b star c is equal to a star b star c. So this is associativity under the binary operation star. This is associativity under operation star. Second, there exists an element, there exists an element E belongs to G such that for all A belongs to G, A star E is equal to A is equal to E star A. So this is called existence of identity element. So we call this existence of identity. We can also rewrite this as in term of quantifier. This is the easiest one. We can, instead of writing the English statement, we can write this in a simple way. There exists E belongs to G such that I use this bracket for such that given any A in G, A belongs to G such that A star E is equal to A is equal to E star. So you can also write like this. And later on, we prove that this E is unique. So this is the symbol which we use for uniqueness. So in next video lecture, we prove that this E is unique. So now, right now, I write there is E in G, given any A belongs to G, A star is equal to A, that is equal to E star. So this is existence of identity element of identity element in G. Now third is for every element A belongs to G, there exists B belongs to G such that A star B is equal to E is equal to B star A. So this is called existence of inverse. So we, we prove that B is the inverse of A under the binary operation star. Or we can also write this for every, the quantifier is for all element A belongs to G, for all A belongs to G, such that there exists, the quantifier is existential quantifier, there exists B belongs to G such that A star B is equal to E is equal to B star A. So in this way, we have written three axioms. First one is associativity, second is existence of identity element, third is existence of inverse. Existence of inverse. So in some of the textbook you found there are four axioms. First one is closure property. So because we have already defined this is a binary operation with a binary operation, so there is no need to write the closure property. It is given. So binary operation is given. So now if because binary operation is given, so if we call groupoid, now definition of groupoid, if a non-empty set G be a non-empty set, and star is a binary operation from G cross G to G, then it is, if star is a binary operation from G cross G to G, it is a binary if star is a binary composition, then it is groupoid. G is called groupoid. It means given any AB in G cross G, so that A star B belongs to A star B. If this belongs to G, then it is called groupoid. Or we can say, we can also call this, if G satisfies the closure property, then it is a group. So example for groupoid is set of natural number with addition, binary operation addition. This n with binary operation addition is groupoid, form of groupoid. Similarly, n under multiplication is also a groupoid. Z under addition is also a groupoid. Z under multiplication is also a groupoid. You can think some more example. Now, second is semi-group. Semi-group, G be a non-empty set, and star is a binary operation G cross G to G. It is given that this is a binary operation. Now, if it is given, then it satisfies the closure property. No need to write. And second, if it satisfies the associativity, that is axiom 1, along with, if it satisfies this property, this associativity, then it is called, it's a binary composition and first axiom of, that is associativity. Under star. So in usual we can say semi group if it is closed under the binary operation. Second, if it satisfies the associativity under the same binary operation. So again, think about the same example, set of natural number addition with addition. So it is a groupoid, we have already discussed. So first property is satisfied. First is done. Binary composition, it is true. Second, associativity. You can take any natural number given any a plus b plus c. Sorry, given any a b c belongs to natural number such that a plus b plus c equal to a plus b plus c. Is it true? Yes, it is true. So set of natural number with addition, it is a semi-group. This is first one. Now come to second one. Set of natural number with multiplication. So n under addition is a semi-group. Is a semi-group. Similarly, think about this. This is also a semi-group. Is a semi-group. Now third one. Think about z with addition and z with multiplication. Similarly, set of rational number with addition, set of rational number with multiplication. Right? So think about these. Now, the third one is, now next definition is monoid. So if a non-empty set G be a non-empty set, and star be a binary operation from G cross G to G, this is given that this is a binary operation, so its closure property is satisfied. Now, along with this, if it satisfies, this is our main definition, definition 1. So if it satisfied 1 and 2, so along with, if it satisfies first and second axiom, satisfies first and second axiom, then G with star is a monoid. Is a monoid. So again, we consider the same example. Set of natural number with addition. Is it a monoid? So first check that is it a binary operation? Yes, we have already defined sum of two natural number is again a natural number. So first property satisfied. Second, associativity we have already checked. Given any natural numbers a b c, a plus b plus c equal to a plus b plus c. Now check third one, identity element. So identity element is there exists E belongs to G such that given any A belongs to, so here we take G to be N. A in N such that A plus E is equal to A, that is same as E plus A. So is it true? Can we find any E? So let us check A plus E equal to A. So we can add both sides by minus A because A and B are natural numbers. So we get E to be 0. Is E equal to 0? This belongs to natural number. Is this belongs to natural number? No. This does not belong to natural. So we cannot find the identity element. So there does not exist. So we can say there does not exist E belongs to N, E equal to, now we can say that equal to 0 belongs to N, such that we can write A plus 0, A plus E is not equal to, we cannot find E. So this property is not. So N under addition is not a monoid. Is not a monoid. Because in addition 0 is the identity element, so but 0 does not belong to natural number. So it satisfies first two property, but third axiom, first two axioms, but third axiom is not satisfied. So an under addition is not an. Now can we think about the same set with operation multiplication? Yes, star operation is multiplication. So a, you can take any ab, you get a dot b, a and b be any natural number given any ab belongs to n, so that a, if we define the binary operations multiplication, ab goes to a dot b, and this is again a natural number. So first property is done by its a binary composition. Second axiom is associativity. You can take any, given any a b c belongs to natural number, such that a into b into c equal to a into b into c. So it's satisfied. And third, because under multiplication you need an element, you need a number which multiplied with any natural number you get the same number. So under multiplication we know that one is the multiplicative identity and one belongs to natural number. So there exists e equal to 1, this belongs to natural number, we can find one such that you give me any natural number, a belongs to n, such that a into e, a into 1, that is equal to a, that is equal to 1 into a. Or you can write a into e equal to a, that is equal to e into a. Here e equal to 1. Is it clear? So n under multiplication is a monoid. Is a monoid. But it is not a group. Sorry, yeah, but n under addition is not a monoid. But n under addition is not a monoid. If we change the binary operation, then it is a monoid. Is it clear? Now come to third example. Z under addition. Is it a monoid? Yes. It satisfies the binary composition plus sum of two integer is again an integer. Now come to the first axiom. Associativity under addition, it holds. Now identity element, yes, 0 belongs to Z. So this is a monoid. Is Z with multiplication is a monoid? Yes, this is also a monoid. You can think about this. Similarly, set of rational number with addition, they also satisfy these three conditions. So under addition is a monoid. Think about set of rational number under multiplication, set of real number under addition, set of real number under multiplication. So they all form monoid. Is it clear? Now up to this, you can revise the content. Whatever we have discussed, up to this, you revise the content, then you proceed. Now next definition is group. So we have already discussed about group. Now let G to be set of natural numbers. So n under addition, because it is not a semi, it is not a monoid. N under addition is not a monoid. So n under addition is not a group because it does not satisfy the second axiom. So is not a group. So group होने के लिए क्या करना आपको? You have to check whether with the given operation, find the operation, it satisfies the first axiom, that is associativity. Second, you have to check the identity, existence of identity of identity. And third, you have to check existence of inverse. Existence of inverse. If G satisfied, if any non-empty set with binary operation satisfies all these condition axioms, then it form a group. But because n set of natural number under addition, identity element does not satisfy the second axiom, so it is not a group. Or we can say because it is not a monoid, so it is not a group. Okay, now is n under set of natural number under multiplication form a group? Think about this and then say yes or no. So we have already checked that n under multiplication is a monoid. It means it satisfies associativity. It satisfies first. It satisfies the second. Second is also done. Now we have to check the third, inverse. So if I give you any given any element, 2 belongs to natural number. Can you find a number such that 2 into there exists B belongs to G such that 2 into B equal to 1? Can you find B? B is 1 by 2, right? Is this belongs to natural number? Is this belongs to natural number? Here G is set of natural number. Is this belongs? No. 1 by 2 does not belongs to. So n under multiplication is not a group. Not a group. Or you can simply say no. Because inverse does not exist. Now same question, Z under addition. So it is a monoid, we have already proved. Now we have to check the fourth property, third axiom, that is the existence of inverse, additive inverse. Now we can say additive inverse. So yes, given any A belongs to Z, there exists B belongs to Z such that A plus B equal to 0 because identity element is 0. So now we can prove that A plus B equal to 0. So we can add minus A plus 0. So by using the associativity, we can write this as, and 0 is the additive identity. So we can write this as minus A plus 0 is minus A. and a plus minus a, because minus a is the additive inverse. 0 plus b equal to minus a. So b 0 is the additive identity, so we can say b equal to minus a. So now we can say that b we can find. You give me a, then I can find this b. B is minus a. A plus minus a to the 0. Now I can write b is the b equal to minus a is the additive inverse of a. So we can also write, now we can modify this. Given a belongs to z, there exists minus a belongs to z, such that a plus minus a equal to 0, that is equal to minus a plus a, right? So now we can prove that z under the binary operation addition form a group. So this is the first example. We have proved that z with a binary operation addition form a group. Now think about that, is z with binary operation multiplication form a group? Form a group. This is an assignment to all of you. Now fourth, the next question is set of rational number with addition form a group? Is set of real number with addition form a group? These are the questions. Now next question, is set of q star with multiplication form a group? Form a group where, now I define q star. Q star means set of all non-zero rational numbers. Rational number. So here I define, instead of writing q, I write here q star. Now q star is defined. This set q star contain all numbers except 0. 0 is not in this. इसमें 0 नहीं है. ठीक है. अब आपको चेक करना है कि क्या ये ग्रुप बनता है अंडर मल्टीप्लिकेशन. एंड द लास्ट seventh question is R star under multiplication form a group? R star, where R star is, again R star means set of all non-zero real numbers. Now think about this. If 0 belongs to R, then what happens under multiplication, right? So instead of asking R with multiplication, मैंने क्या पूछा आपसे कि R star. So R के बारे में नहीं पूछा है. आप ये सोचना कि R को अगर हम सेट R लें अंडर मल्टीप्लिकेशन, तो वो ग्रुप क्यों नहीं बनता? Where R is set of real number. मैंने इसमें फोकस, मैंने जानबूझ के इसमें स्टार में डिफाइन किया कि सारे के सारे नॉन जीरो रियल नंबर्स हैं, इसमें जीरो इंक्लूड नहीं है. सिमिलरली क्यू स्टार में जीरो नहीं है, फिर ये ग्रुप बनता है कि नहीं बनता है, राइट? सो ट्राई दीज क्वेश्चंस, दीज आर वेरी वेरी इंपॉर्टेंट क्वेश्चन, और ये बेसिक है. अगर आप इन सारे के सारे जितने भी मैंने क्वेश्चन डिस्कस किए हैं, अगर आप इनको अच्छे से करोगे, अच्छे से आप इनको समझोगे, देन इट विल बी वेरी वेरी हेल्पफुल कि आपको अलजेब्रा समझ आएगा और आप उसको इजीली आप उसको अंडरस्टैंड करेंगे. So in next video we will discuss some more concept, and with these examples. So we discuss some more examples, but usually we pick these examples. So we will meet in the next video. Have a nice day. Thank you.